idea that came up too. But so we could do like all of them mixed into one. And Death of God in one party. Murder mystery. Yeah. No, yeah, probably not.
So the real question, as an engineer, are you bringing like a super flashlight?
Tonight? No, I don't think I have a super flash. I do have a big, like, hit somebody over the head with a kind of flashlight, though.
So the police style baton end.
Like, it is like, it's a mag light. Like, I got it for Christmas, and it was like my whole stocking. Like, yeah.
You should have one of those, like, the ones that are on trucks that just illuminate, like, the world.
Yeah.
Just have one of those on the stick.
Yeah. See, I'm trying to fit in, though. That's the thing. Like, when I gotta do social stuff, I try not to be the obvious engineer in the group.
I try to win, so.
Yeah.
So
Yeah, right?
I played $6.
10 plus the fees.
Professor, why don't we build a helmet that will sense the eggs?
I did get ripped off. Yeah, right. I think that would take me longer than in like 2 hours from now. Plus, I got to teach you guys steady state response performance from chapter 4. Yeah, it's going to be fun. This is the third and final of the okay of the performance chapters that we're discussing. So there were 3 different chapters on performance. The first was on the stability performance. The second one was on transient response performance. And this third one is on steady state response performance. So this is the last of the performance ones, and then we're going to get into how to do root locus analysis and design in a minute, next week. So after the transient response has settled, so that was what we looked at last chapter, the transient response, like the rise time, settling time, percent overshoot, etc. That is, once the system has reached steady state, the system may or may not be in a desirable state. So you might have commanded that the robot arm go to 32 degrees, and it ended up being at 29 degrees, and that's where it's going to stick, okay? That would be steady state error, okay? So if the response asymptotically approaches any state other than that commanded, it is said to have steady state error. These arise from 3 primary sources. 1, nonlinearities like backlash in gears. We're not going to explore that in this chapter, in this class, really. 2, disturbances from those from the environment, which we will actually deal with indirectly. You can deal with these in the same way that we're dealing with the third one. So we're kind of taking care of 2 as we do 3, which is input, commands type, and plant dynamics. So the dynamics of the plant and the controller and the command that you give to, like, say the robot arm, like, this is the position that I want you at, those 2 factors come into what the steady state error will be. So for instance, if you say go to 30 degrees and it goes to 27 degrees, like, that's a steady state error. But also, maybe you say your command is a linearly varying position with time. Maybe you're like telling it to go around and around in circles. And so your command value is changing, say, linearly in time. That would be a ramp sort of command. A different type of steady state error might arise in that situation. We're going to actually look at 3 different command types and characterize the steady state response using those. Okay, so we're going to focus our attention on item 3, but item 2 is similar. The disturbances you can deal with in a very similar way. Okay, any questions? All right.